Hey everybody, welcome back to another round of physics, and yeah, let's get going. Displayed for you here, I have a different type of circuit, and you can see we still have a battery, a capacitor, and a resistor. And what I am doing right here is that we are charging up the capacitor with the battery. In other words, we'll leave this switch like this, and at some point the capacitor potential is equal to the battery. Now, how this is helpful is that this gives us a starting value for the total amount of charge stored on the capacitor. Namely, the charge should be something like Q is equal to the potential of the battery times the capacitor itself. So that's the first part. Now, here's where we're going to go. Now that the capacitor is fully charged or fully energized, we're going to take that switch and we're going to flip it to the other terminal. Okay? In other words, we are going to disconnect the battery from the circuit and connect the capacitor in series with the resistor. If you prefer, you could think about taking that circuit and drawing it something like this, where we have the resistor R, we have the capacitor. Okay. And this is the situation we want to consider, and this is often referred to as the discharging capacitor or a discharging circuit in general. Okay. And let's go through and see if we can apply Kirchhoff's laws to analyze this circuit. Well, first of all, thinking about how we charged up the capacitor in the first place, we know that the top plate must be the high potential side, the bottom plate the low potential side. And I should mention that if you don't know how the capacitor was charged up, just arbitrarily choose a side, okay? And then be consistent with it. Okay. Same thing applies. The only reason that I showed you this circuit is to give you some conceptual idea of how the charging process could be done. Okay. Now that we have the high and low potential sides, you could think of the capacitor is the source of energy in this circuit. And so the current must flow clockwise around. I'll call that I. So that this must be the high potential side and the low potential side of the resistor. Now we're off and running like a bale of turtles. We know that the potential jumps must be equal to the potential drops. And so we see that the potential on the capacitor must be equal to the potential drop across the resistor. And substituting in our expressions for the potential drops, we have the charge on the capacitor divided by the capacitance must be equal to the current running through the resistor times the resistance. We have to be a little bit careful because these two quantities now refer to different things. Okay. And let me explain to you how that is. The total charge on the capacitor, what I've labeled as QC, that must be equal to the maximum charge, right? The starting charge that it had, okay, minus some amount of charge that has been lost. And the question is, where did that lost charge go? Yeah, good. It got removed from the upper plate, traveled through the resistor to recombine with the bottom plate. Okay? In other words, this charge that has left the capacitor is responsible for the current that I have here in my equation. Okay? So we have to be a little bit careful. Basically, this QC and that I, that current, they refer to slightly different charges. Now, how it's related, of course, if I take this equation for the total charge on the capacitor and I differentiate, I get that the change in the charge on the capacitor per unit time, well, this Q max, that was a constant. In fact, that's what we have up here, this VC, that's Q max. And so what I have is that the change of the charge on the capacitor is equal to the negative of the lost charge. Okay. Or a different way to say it is the change on the capacitor charge is negative the current. Right, I can rewrite this. The change of the charge on the capacitor is equal to the negative current flowing through the resistor. Okay. And that piece we'll need. In fact, if you just blindly substitute in I is equal to dq dt, okay, if you automatically assume that that current applies, that current and the charge on the capacitor are the same, okay, you'll miss that negative sign, and what you'll find out at the end of the day is that the current blows up exponentially instead of going to zero. Okay. So be careful there. That is the negative sign that I always tend to drop. I always forget that negative sign. Well, with that, what we can do, I'll say IR here. Okay. With that, what we'll do is let's make that substitution. So I have the charge on the capacitor divided by the capacitance is equal to the negative change in charge on the capacitor per unit time times, and I'll put the resistor out front here. Okay. And again, here we notice that we have a first order homogeneous differential equation with constant coefficients, and this equation should be separable. Take a minute while I rewrite that equation on a new slide. Take a minute and solve that equation. Now, if you're not done now, go ahead, pause the video. Okay? Well, here we'll just go ahead and rearrange. I'm going to get the q's onto one side. So what I end up having is dq over qc, I better keep my subscripts, is equal to, and on the other side I have dt divided by rc, negative. You say, well, that looks familiar, right? This negative dt over rc looks familiar. And in fact, I go ahead and integrate, and I get that the ln of q C equals negative t over rc again, plus some integration constant. Or at the end of the day, I get that the qc is equal to some constant a e to the negative t over rc. And we see that that time constant, rc, comes back in. Okay. Now, we already know what a has to be. We argued when we were charging up the capacitor, we hit the Q max, the starting amount of charge on the capacitor was the capacitance times the potential of the battery. Or a different way to say it is that time equals 0, the starting amount of charge is equal to CV. Well, in order for that to be correct, that means that A has to have a value of the capacitor times the battery potential, e to the negative RC. There we go. Boom. Oh, that's a bad line. Boom. Here is the equation which tells us how much charge is on the capacitor as it discharges. And again, you can see there's an exponential behavior quickly approaching 0. Well, you could say, Greg, what about the current flowing through the resistor? I go, yeah, that's not a problem. Remember, we said that the current flowing through the resistor is the time derivative of this with the negative sign. So let's go ahead and do that. Well, of course, the potential is a constant, and taking the derivative of an exponential just simply results in the same exponential. I should say e, not the exponential function is maybe how I should say it. And then we have to chain rule it, right? We still have to take a derivative of the exponent, and so I get a 1 over RC here with the negative sign. You say, oh, goody, goody, look at that. The C's cancel, and I get that the potential divided by the resistance e to the negative t over RC. In other words, not only does the charge on the capacitor exponentially decay to 0, but the current running through the circuit also exponentially decays to 0. Pretty cool, huh? Now, like I said, notice that regardless if you have a charging or discharging capacitor, you have this e to the negative t over RC come into play. Okay? And so I don't tend to memorize all 4 of these equations, like this one, and then the 2 equations from the past video. I don't tend to memorize those. Okay. What I tend to do is I think about the behavior of the capacitor at short time intervals and at long time intervals to remember which equation goes where. That will tell me if I have something like a 1 minus e to the negative t over RC, or if it's just e to the negative t over RC. That's the first thing. Now you could say, but wait, Greg, how do you know about the coefficients? Well, the coefficients out in front, I get those from thinking about units. Okay? I know that the units of current have to be in amps. So whatever's out in front better have units of amps. Okay? And then from that, I can figure out, okay, well, it's got to be thinking about Ohm's law. Okay, it's got to be V over R. Or if I know it's a charge, I know the units out front have to be coulombs. And so immediately I know I have to have something like a potential times a capacitance. Okay. So again, I don't tend to memorize them. There's just way too many places where I can make mistakes. I know that it has to have e to the negative t over RC in the expression. And then I think about the short-term and long-term behavior to figure out the form of the function. And then lastly, think about units in order to come up with what coefficients go out in front. Okay? Well, I think that that's plenty for this video. Like I said, I just wanted to have a very quick video showing you the discharging capacitor case. So we'll leave it there. Thank you for your attention. Keep up the good work. I'll see you next time.